Okay, let me start. Today we're going to talk about the neural network, basics, representation, backpropagation, and activation function. Actually, this today's lecture is the starting of the deep learning part in our course. Actually, in the first part in our course was the conventional method or the traditional method, something like the linear regression or the logistic regression. From today, we will just talk about the deep learning related work, such as the neural network or other things. So, okay, before starting, let's see the success of the deep learning. I think the most of you already know the deep learning and why deep learning is important and what happens after deep learning. So yeah, let's see here. Yeah, so in deep learning, by using the deep learning, there are so many possible technique where the application was reformulated, right? So as you can see here, this one, so the artificial intelligence related conferences or the journals has been increased dramatically from 2012, where when the deep learning was started practically. So in 2020, right? In this year, there was the 12,000 papers submitted to CBPR. So CBPR is the one of the most popular and the state-of-the-art conference in the computer vision field. So as you can see here, deep learning is getting bigger and bigger. Okay, so deep learning was success in the several kinds of the application or field. Actually, I would say the most of the application or the technique or the the industry will be reformulated by using the deep learning. So one of the most popular example is the image classification. So as you can see here, as a human like us to recognize what is the semantic meaning of this image. So there is one people, and these people can track the cycle and or take cycling, something like that. But the goal of the image classification is how to train the machine or the algorithm to recognize this image as a semantic label in terms of the semantic label automatically. Okay, so this is the goal of the image classification. So in image classification, the deep learning or the convolutional neural network or just the neural network was has been used from the 2012 from the AlexNet. So AlexNet was the practical starting point of the deep learning. So we will just see what it is, but I can just say that the in image classification task or the image classification application, deep learning make a big breakthrough. So after that, so many papers have been proposed to solve the image classification problem using deep learning. Another example is machine translation, but before move on to the machine translation, this is just a leaderboard for the image classification. So before 2011, there was the handcrafted model just based on the SVM or something like that. But from AlexNet in 2012, there were large performance gap between the 2011's method and AlexNet. So after that, so many papers or so many methods have been proposed. In 2012, some method even outperforms the human's performance in image classification task. So where are we now? We are now in 2012. So you can imagine there was how much progress during this decade. Okay, So anyway, image classification is the one example. Another example is the machine translation. So machine translation is built in Google Translator. So I guess some of you or all of you will use the Google Translator to translate your language to the another language, such as the Korean to the English or the English to Korean, something like that. So in machine translation, the deep learning is the core algorithm to develop the practical translator. Another example is the speech recognition. So as you can see here, if we have the given audio signal, we can recognize the semantic meaning from this audio signal or the relationship between the audio signal. For example, if you imagine the Siri in iPhone or Clover in Neighbor, so those kinds of methods based on the deep neural network to recognize your speech from natural audio signal. Okay, so this is the another example. One more example is the speech synthesis. So if you have the one voice style, then you want to synthesize a new voice sentence, then in this case we can use the deep learning also. For example, if you have the Trump's body voice signal, and then you want to synthesize a new narrative with the Trump voice signal, you can do by using the deep learning. So it means that we can make a fake news using the Trump's voice to by using the deep learning. So this is very simple or the fun examples of the speech synthesis. Another example is the game playing. I will skip this one. I will skip the AlphaGo because all of you maybe heard about this from every class and every newses, so I will skip this one. But anyway, so in game playing, the deep learning have make some very fundamental and very dramatical performance improvement. Okay, so and then there are so many applications by using the deep learning. So why the deep learning start to make the very big or the very impactive effect on our daily life? There are three kinds of the lesion. Actually the neural network, which is the core algorithm in deep learning, was invented in 1920 or 1921, something like that. But the real starting of the deep learning is from the AlexNet in 2012 from here, right? So after that, everything is changed. So there is three regions. The first one is the algorithm, because the authors in the AlexNet paper tried to make the very well designed neural network to recognize the image. So this algorithm was very successful. So most of the paper after AlexNet tried to reformulate the AlexNet network architecture tailored to their own application. So this is the first reason. Another reason is that the data. So nowadays we can easily access so many image data set from Google or video data set or YouTube. So nowadays we can access so many data to train the neural network. So this is another reason. The final one is the computation module. So by developing the powerful GPU or the computation architecture, computer architecture, so we can compute the deep learning related computation very efficiently comparing to the previous one. Okay, so by using based on these three kinds of the finding or these three kinds of the success, nowadays we are living in the deep learning world. Okay, so until last week, we will discuss about the traditional learning algorithm. Let's say this is the traditional learning algorithm, such as the what's that? Logistic regression or the SVM, something like that, right? So the x-axis means the amount of data, something like the input feature xn with the label yn. So yeah, this is set of the input pair. So as increasing the number of data, the performance, the performance by learning algorithm will increase, something like that. But this performance will be saturated to some values if we use just the traditional learning algorithm. But if we can use the if we can just use the neural network, the performance is also increased by increasing the number of data, but we can improve the performance as increasing the number of data. Or if we can use the very large neural network, which is just called the deep learning, we can dramatically improve by increasing the number of data. Okay, so it means that if there is very small training data, the performance gap is marginal, right? But if we increasing the number of data, the performance gap between the deep network and deep learning and traditional learning algorithm will be increased. So let's say this is the large neural network, or just called the deep learning. Let's say this is the small neural network. Yeah, let's just say small neural network. Okay. So today we will talk about what is the neural network and what is the deep learning. Then what is the difference between the conventional learning algorithm with the deep learning. Okay. Okay, let's start with the binary classification. So let's start with a very intuitive example, image classification. So there is the input image, something like that. As a human like us to recognize this image is cat or not, right? But as a machine or as a deep learning or as a learning algorithm, they just see this image as a pixel value, something like this. So let's say this is the input vector, right? So for example, okay. For example, the input vector is something like 105, 112, 108, something like that. From here, right? So let's say the size of the image was the 200 by 100 by 3. Then the size of the input vector xn is the 200 by 100 by 3. Okay, so the problem is that from this vector xn, we want to estimate the yn, the class label. So class label will just the binary signal 1 or 0. So the goal of the machine learning is to build a new function that estimate the yn, which is close to the ground truth yn. Okay, so this is the main the goal of the machine learning. So if you remember the two popular method, linear regression and SVM, for the classification, the problem formulation was something like that. Okay, we have a training data set xn and yn. xn might be vector. The number of samples start from the 1 through the large n. Then what you want to do is to estimate the parameter w in our machine. For example, if we use the linear regression, there's a parameter w here, right? If we use the SVM, the parameter w is here, right? So what I want to do is to design our mapping function between xn and yn related to the w, and define the loss function and minimize the loss function to finding out our learning parameter w. Okay, so if we have the new x in testing set, we want to classify a new yn, even though without knowing the ground truth yn. Okay, so by designing the loss function here there is two kinds of the method, linear regressions and SVM. Okay, let me generalize this kind of the classification problem. Given xn input feature and yn output label, we want to define mapping function, right? So mapping function f xn with w, in case w is learnable parameter, right? Learnable parameter. Then from fxn, w, we want to define the loss function, right? Or the cost function. So this yn from training data set, right? Something like this, something like that, right? So by defining the cool loss function, something like MSE or what is that? Logistic regression? Logistic regression cost function? Logistic regression cost function? Or hinge loss? Something like this. We can formulate several kinds of the traditional method for the classification problem, right? So, but in those traditional methods, they just assume the very simple mapping function. For example, in linear regression, actually, this is not a linear regression. This is the logistic linear regression, right? Logistic linear regression. If you can see the lecture 3 here, yeah. So this is the simple simple examples of logistic regression. So this is a logistic regression. Anyway, so in here they just to use the very simple mapping function like the W transpose times Xn, like this, or in SVM, they also compute the very simple mapping function, right? But in neural network, they want to focus on here. They want to develop a more complex mapping function. Complex mean not about the number of parameter, but just the well-designed mapping function. Okay, so today we will see what it is, but the main difference of the conventional logistic regression and SVM and neural network are here. The designing of the designing of the mapping function. So in other words, we can use the same loss function we already talked about in the previous lectures. We can just use these loss functions to train our neural network, or the deep neural network, or the convolutional neural network, or deep learning. So the core difference of the deep learning here. Okay, so let's start. So the core of the deep learning is the perceptron. Okay, so what is a perceptron? So the concept of the perceptron is invented in 1984 by Frank Rosenblatt, right? So he was inspired by neurobiology. So our brain consisting of so many neurons. So one neuron looks something like that. Okay, so one neuron have the some input and output with some kinds of the module here. So he want to reformulate this neuron looks something like this one. So it means that if we can reformulate our brain, our neuron, something like this, this former one, then we can do similar thing. We can do similar thing that our brain do. Okay, so it was starting point of the neural network. Specifically, if you can see one neuron in our brain, it consisting of the input here, output here, with some parameter, right? So similarly, we can define the input and output with the complex or the linear combination of the input and output, input and parameter, right? So this is just called the perceptron. So actually, this perceptron, if you can see this perceptron, the shape of this one is really similar to the logistic regression one. Actually, it's exactly same if we considering the disactivation function. Okay, so we will see what it is, but this perceptron is one basic module in the neural network. Okay, so let's see the difference between the conventional linear regression problem and the two-layer neural network. So in here, let's just considering the binary classification case. In this case, input xn is in R, let's say RT space. Okay, so in this case, d is equal to d is equal to 3. Then what is the W in here? W in R 1/3, right? Let's say just t, because d is equal to 3, right? Then the output f is just color value. Okay, just 1. So this is the probability of the binary classification, right? So in here, in linear regression problem, linear regression, in linear regression problem, we can lead through the linear regression, something like that. From the input values, let's say xn consists of the x1, x2, x3, something like that. Then we define w1, w2, w3, something like that, and aggregate those values xi and output f, like that. So this is just a linear regression, right? Then this one linear regression can be the one module in the two-layer neural network. So let's say this is a two-layer neural network. So this left-hand side, the neural regression module, will be something like that. Okay, so this one, and this one, right? So yeah, here. So let's say this is the H1. So H1 is the sigma I W I X I, something like that. Okay. So if you see the just one module here, this is similar to the linear regression, but one difference is we considering the nonlinear mapping function, or the nonlinear mapping, or the activation function. So we define nonlinear, some kind of nonlinear function. So we will see the kinds of the nonlinear function in the following, but in this case, just yeah, let's define here. Okay, so let's define something like that. Let's say the max function is g define something like max. Okay, so this is the one example of the activation function. Anyway, so by using the linear combination of the input and parameter w1, w2, w3, something like that, then we can compute the one output here, right? But unlike the linear regression problem, we can compute the another output by using the another linear let's do something like that. By using the another combination of the input and the another parameter output, another parameter, something like this, and something like that, right? Right. In other words, how many parameters are here? How many parameters are here? How many parameters? Four by three, right? Why? Comparing to the linear regression that has the 1 by 3, they need another layer, something like this. So let's say this is H2, H3, and H4. So we need 4 times more parameter. Then from here we can build one more linear regression perceptron module, something like that. So in this case, W2 in the R, what's that, 1/3 space, like that, here. So comparing to the linear regression, this two-layer neural network has the more parameter, so we have the more capacity to train our machine. So we can deal with a much more training data set because we have the much more network capacity. So this is just called the two-layer neural network, right? So this one is just directly extended to the multi-class case. So let's say multi-class case. So if you remember the logic regression lecture in lecture 3, so there was a multi-class case, right? So how can we do that? So by designing independent training parameter, right? With the 3 output, right? In SVM, we can do similar things, right? Where is the SVM? MultiClass SVM. Where is that? I can't find, but anyway, so we can do similar things by using SVM, but as you can see here, the linear regression problem can connect it or something like this, something like this. Okay, let's use different color. Something like this, something like this, something like this. And similarly, we can define our neural network for the multi-class output case, something like this one with this one. So there will be the 3 output here. Okay, so this case, this called the hidden layer, and this mean this called the input layer, this called the output layer. Okay, so this is the comparison between the original linear regression and our two-layer neural network. So we can just extend this two-layer case, something like that. Actually, if we have the input xn, there are w1 here, w2 here, right? With the nonlinear function here, max, this one, right? So we can represent our two-layer neural network something like this. So comparing to this linear regression, it looks much more complicated, right? So in other words, we can extend this one to the 3-layer neural network, like that. In this case, we need one more parameter set, W3, right? So here is the definition. The neural network is the very broad term, so these are more accurately called the fully connected network, or sometimes a multi-layer perceptron, right? Because the perceptron is just one module, something like this, but because neural network the stack of the perceptrons, so this neural network just called the multi-layer perceptron, or NLP. So in this course, we will use the discrete terminology, neural network, convolutional, fully connected network, and multi-layer perceptron to represent this one. Okay. So this is a representation of the neural network. So here, comparing to the linear regression, neural network two-layer case and three-layer case has this nonlinear mapping term. So this function is called the activation function. So what does it mean? Before starting, what if we try to build a neural network without this one, without activation function? This one is just will be this one, right? Because there is no nonlinear activation function. Then if we can suppose W3 is equal to W2 times W1, then the problem will be F is equal to W3 times Xn, right? So this one will be the so linear regression term like this, right? So we can end up with a linear classifier here. So in other words, by using the activation function, we can do much more things comparing to the linear regression algorithm. Here's the thing. So by using the activation function, we can add a non-linearity to network the function. So it means that if we just use the linear regression, we can just considering the linearly separable case, something like that can be separated by the straight line, something like that. But if we can properly adding the nonlinear activation term or the activation function, something like that, then we can make a new decision boundary looks like this. That considering the non-linearity in the training data set. So that's why we are using the activation function. So activation function is also very important term in the neural network. This is a very popular. This is the popular examples of the activation function. The first one is the sigmoid, right? So we already see what the sigmoid is. Okay, so if you go back to our lecture 3, where is that? There was the sigmoid function, looks like this, right? So here, by using the sigmoid, we can deal with the nonlinear mapping between the input training data set and output label, right? And another example is the tangent, the activation function. The shape is looks like that, and max out mapping function it looks like that. This, and there's one more thing. So ReLU, eReLU, liquid ReLU, like that. So comparing those kinds of things will be beyond our course, but I would say this ReLU function is a good default choice for most problem. So comparing to the sigmoid, this ReLU function is the some kind of approximation, right? Approximation, but as you can see here, the computation of the activation function is much easier or much simpler than the sigmoid. So because in deep neural network there are so many nonlinear activation function here. So the computational complexity is really important. But if you use the sigmoid, it is impossible to train the very large scale network. But if you use the ReLU function, which is very easy to compute, we can dramatically reduce the computational time while preserving the network output performance. Okay, so this is the activation function. So usually in neural network, just use the ReLU activation function. And recently, sometimes some of paper use the liquid ReLU. So liquid ReLU is the generalized version of the ReLU paper. So if you're interested in this one, please find out what it is. I forgot the name of the paper, but yeah, please check. So what was that? Okay, so this is the activation function. Okay. So from here we discussed the perceptron and the neural network with the activation function, right? So here, so to summarize, the two-layer neural network looks like this, right? Because there is the two layer, the one layer and two layer, and there is a three-layer neural network case because there is a three layer, one layer, two layer, and three layer. So we can say that this figure represents two-layer neural network or one hidden layer neural network. So this is the hidden layer. This figure shows that this is the three-layer neural network or two hidden layer neural network. So it means that hidden layer. Okay, so this is simple toy examples of the neural network. Actually, nowadays, deep neural network means there are 100 or the 1000th layer. They consisting of the one. Okay, let me show some example. Okay, if you remember this figure, the size of the input is something like 660 000, right? So this is the input feature extent. Then there is a neuron. There will be some kinds of hidden layer and output here. So the state-of-art method in image classification consisting of the 1000 hidden layer with so many hidden node, something like that. So it might be this is very infinite number of the parameter. There are almost infinite number of parameter to classify the one image as a class label. So it will be really hard to optimize. So we will discuss how to optimize this dramatically large parameter. But anyway, so deep neural network are very big set of the neural network. Okay, so let's talk about how to estimate the network parameter. So if you remember where is that? Yeah, here. If you remember the logic regression and SVM, the objective is to find out the W, right? By minimizing the loss function, right? So in neural network, the goal is also same. Okay. In neural network, this line means the parameter W, right? So what we want to do is with the input layer and output layer with some kinds of the loss function, we want to update or we want to compute this parameter, network W parameter that generate the most significant output in terms of the loss function. Okay, so our goal is to find the value for each straight line here, 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 something like that. Okay, so then how can we do that? How can we do that? The very popular method is the gradient descent, right? So we already know what was the gradient descent, right? So okay, let's go back to lecture 3. So where is the gradient descent? So here, so as you can see here, the gradient descent defines something like that. So if you want to minimize this loss function with respect to the W, network parameter W, then you can iteratively update the each network parameter by using the gradient, right? So we already discussed why we need a gradient, right, to update this parameter, right? So okay, let's say this is xn, this is the mapping function, right? Mapping function w xn with the w value, right? Then and there is the loss function like this. Then loss function defined with the mapping function from the input xn and ground truth yn, right? So loss function will several kinds of things, right? If you remember this page, MSE, logistic regression, hinge loss will be the candidate for the loss function. Anyway, if you have the loss function, the gradient descent is to repeat, to update of the each parameter W with the gradient of the final loss function in terms of the parameter W. Okay, so it means that this every parameter, this is the one parameter, this is a one scalar value, this represents one scalar value, this represents also one scalar value, right? So we have to compute the gradient of the loss function, final loss function, in terms of the each parameter. So we have to compute the gradient of the loss function in terms of the with respect to this one, and with respect to this one, and with respect to this one. Okay, so and then we will simultaneously update all Wj, right? So if you remember this one, where's that? Yeah, here W1 looks like the 4×3, W2 looks like the 1×3. Okay, so the W consisting of the W1 and W2, right? W1 was the 4×3, W2 is something like 4×1, 1×4, right, like that. So this is very large. Or here's problem. So if you remember the okay, I will show you this example. The size of this neural network are so big, so it's really hard to compute the gradient of loss function for each parameter W value, right? So in other words, computing the gradient for each W, it's very tedious and lots of matrix calculation. Another limitation is that what if we want to change the loss, then we have to derive from scratch, so it will be the one more problem. Another thing is that it is not feasible for very complex model. So nowadays most deep neural network based on the very complex model, so it is hard to compute the gradient, something like this. Okay, so we need a more clever way to solve this problem. So to solve this one, we introduce the computation graph and backpropagation terminology. So let's see what it is. So yeah, here. Okay. So where is that? Yeah. Okay. So let's think about this neural network as a graph. Okay. So in this case, each one will be the node, and this one will be the edge of the graph. So you don't need to study the graph theory to in this one, but just you can understand this looks like graph, right? So and then here's our goal. So okay, so f of x, y, z is equal to x plus y times z, something like this, right? Then we want to compute the gradient of the f and with respect to x, and gradient of the f with respect to y, gradient of the f with respect to z. Okay. Then let's find out a more efficient way to compute this one. Okay. So first of all, the computation graph looks like this. So this one can be decomposed the plus and multiplication, right? So input x, y, z here, up, f here. Then how can I compute this one more efficiently? So first of all, let's say x is equal to -2 and y is equal to 5, z is equal to -4, right? -2, 5, -4. Then let's say this is the q, right? So q will be the what? Q will be the 3, right? Then 3 by 3 times -4 will be -12, right? Then what do you want to do? We compute this one, right? So but compute this one directly is really hard to compute. So we want to compute gradient this one first, and then use the last gradient to compute this one. Okay, let's see the detail. Okay, so we already know the q is equal to x plus y, right? Then what is the gradient of q with respect to x? 1, right? So gradient of q with respect to the y is equal to 1, right? Then and f is q times z, so f q is equal to z, and f z equals to q, right? Okay, so we already know this property, right? Then first of all, from here, what is the gradient f with respect to f? 1, right? Then we want to find out, okay, let's use different color. Then we want to find out gradient z of F, right? Then here, yeah, something like this. Okay. So this is the gradient y. Something like this. Okay. So how can I compute this one? So from here, we already know that what's that? Yeah, F like this, right? So we know that this one represents something like this, right? So we already compute this one as a 1, right? So this is just gradient f with respect to z, right? What about this? We already know gradient q by f, right? Q by f here, right? Then we know gradient y by q here, right? Then without computing this one directly, we can just compute this one by this one. So we already know this one and this one. Then we can directly compute this one, right? So, and then what about this? This is the q times f and f times the q x, right? What is that? Here, and this one here. So it means that this one is just z times 1, right? This one is just q times 1, right? Just 1, just q times z. Okay, right? So in other words, to compute this one, we want to compute this one directly rather than we can compute the gradient from here, then backpropagate this gradient to this one, and this one, right? So in other words, rather than computing this one directly, we can compute the from last one to the first one by using the some property. So this is called the chain rule. Okay, so in other words, to compute this gradient, we can use this gradient to compute this gradient. So this is called the chain rule. Okay, so let's see the detail. Okay, here is the generalization of the update of the parameter. Okay, this is the input xn, and this is the output, right? Then with this output, we can define the loss function here, right? Okay, so what we want to do is update this value, right? So this is just one parameter w, right? So there are parameter, so a number of parameter, right? So parameter 1, parameter 2, parameter set, parameter 3. So the overall parameter is the 1, 2, 3, right? Then what we want to do is the compute the gradient of loss function for each. Okay, let's say it's w1. Just one parameter. Let's just use the parameter that right there. So we have to find out this one, right? So this is a problem. So what we want to do is to compute the parameter here. Then by using this one, we can update this one and this one and this one. Then by using this one, we can also update this one by using this one. Okay, so this is the general idea of the backpropagation. Okay, so rather than computing the gradient gradient loss with respect to the w how can we read this w, then rather than computing this one, but we can compute the gradient from here, or to compute this gradient, we can follow another line here, another line here, another line here. Okay, so by using this backpropagation algorithm, we can efficiently update this parameter from input layer to the output layer. So this process is port process. This update process is a backward process, or forward propagation and back propagation. Okay, so this backpropagation is the key algorithm in updating the network parameter in dim network. Okay, so let's see the detail. So let's think about one module. Let's say X, W, and H, right? So this one is represent something like that, right? So with xn and w, so parameter, right? Right. So this parameter here, right? In this case, this function is just compute multiplication, right? And this is output, right? So to update this parameter w, we have to compute w l. This is loss function, right? Right? Then how can we do that? If we have the gradient of loss with respect to the h, then we can represent this one by using the h L and W by H. Okay, so we already have the gradient here, here we only need to this one. Then what is this? We can compute here. From here, W H is equal to X, right? And X H equals to W, right? Then here, right? So this gradient is compute this one and this one, right? So by using this one, we can update this parameter. So we can update this parameter, right? So in other words, if there is a loss signal, gradient signal from this layer, loss layer, something like this, then we can just update. We can just update of this parameter by using this loss function and relation gradient between H and W, right? Okay, so now we can update this one. Then what about this? What about this? So if you consider this one, it will be the new X and new H. Then to give the gradient to the another lower layer, we also have to know the gradient of this one. So in other words, we also have to find out the gradient of loss function with the X to compute another term, something like another term, something like this. Okay, so this one is also defined the similar way with this H L with the what's that, X H, right? So this one is here and this one is here, right? So this one is just W, this one is double X, right? So by using this gradient and this relationship of this module, we can compute this one and this one very efficiently. Then by using this one, we can update another node using this one, because this is the previous gradient with respect to the X, right? So this is the one module for the backpropagation. So here is the definition. So in this case, this is called the upstream gradient, and this is called the local gradient. And this one and this one called the downstream gradient. Okay. So by using this upstream gradient, local gradient, and downstream gradient, we can define each backpropagation step. So by using the forward propagation and backward propagation, we can update every W here and here. So which means this is the network training procedure. Okay, so this is a core algorithm for updating the parameter or training the network. Okay, so before finishing, I want to emphasize several things. The first one is related to derivatives. So if the input is the scalar and output is also scalar, the gradient is just a regular real value, right? For example, this means that for x change by small amount, how much will y change? Okay, so this is just a very simple simple meaning of the derivation, something like this, right? Then what about this? If if input is the vector and output is vector, then gradient, the derivative will be gradient. So in other words, the gradient of y with respect to the vector x will be also vector, right? So it means that for each element of x, if it change by small amount, how much will y change? So this is the meaning. Or if input is vector and output is vector, then derivative will be Jacobian. So the gradient of the vector y with respect to the vector x will be the matrix size of n by m. Okay, so it means that for each element of x, if it change by a small amount, how much will each element of y change? Okay, so this is the meaning of the vector by vector derivation. So I will upload some kinds of the material related to this vector derivative, because this is related to the mathematics class. But by using this vector by vector derivation, we can define a new commutation graph and backpropagation. So comparing to this one, if we can, this is just one vector x, and this is just one vector w, right? Actually, vector and matrix is the same, right? Because if we reshape the matrix into the vector, the values will be exactly same. So let's say this is just vector, right? Then let's say this is output h. Okay, this h w, right? So if we can use the vector to vector notation, whose derivative is the Jacobian, then we can define the backpropagation in the node level. So it means that the local gradient, this upstream gradient, this upstream gradient will be the vector, right? Then where's that? This local gradient will be Jacobian, right? Because this is vector and this is vector. In upstream gradient case is the gradient. Why? Because the loss output is just the real value, right? So loss is just real value, so this is just the gradient. And so what is that? The downstream gradient. Okay, so downstream gradient is also gradient. Why? Because to compute this one, we have to multiply this one and this one, which will be the just the vector, right? So just gradient. So this is just gradient. Okay. So this is the backpropagation algorithm to update the network parameter in neural network. Okay. Okay. So this is just very simple definition of the neural network and the multi-layer perceptron or deep neural network. From next week, we will start the convolutional neural network. Actually, the heart of the deep learning is the convolutional neural network. Actually, this one is not a convolution. This is just a fully connected module. This is just a linear regression module. But the convolutional neural network is more efficient way to compute the output by using the deep neural network. So actually, this is the main algorithm in the AAA601 or the most state-of-the-art method or state-of-the-art deep learning method. So let's discuss this one from next week. Okay, thank you.